let's discuss the implications of incorporating a derivative controller. Okay, so we'll be using a controller which provides derivative control only. Okay, so the block diagram will look something like this. So this is the plant. So for the sake of simplicity, we'll assume a first order plant. So as you can see, this is the transfer function of a prototype first order system. So here we have the controller. So since this is a derivative only controller, its transfer function will be S times K D. This is something that we have already discussed. So then we have the usual summing block. So R is the input. Okay, so we have the error signal here. And again, for the sake of simplicity, we're assuming a unity feedback control system. So this is what a closed loop feedback system incorporating a derivative controller looks like. Now, if we evaluate the transfer function of the closed loop system, that will look something like this. I need to change my chalk. So if you carry out the algebraic manipulations, you will see that the overall closed loop transfer function will look something like this. So we'll have S plus KD plus, that means I'll have KD plus T, which is the time constant of the system. You can take a moment to verify whether this indeed is the closed loop transfer function of this kind of a system. So I'll rub off this block diagram. Now let's assume that the system is subjected to a unit step input. So in that case, R, so as you can see, this S and this S cancelled out, so we're left with this. So if I take the inverse Laplace of this term, I'll get the time response in the time domain. So, but before that, I'll make a few simplifications. What I'll do is that I'll divide by this term, that is KD divided by KD plus T. So what I'll have here is just S, and this term will now be 1 over so now it is in a form where the inverse Laplace transform can be obtained easily, and the inverse Laplace looks, so we'll have the response in the time domain, which now we're using small letters for that. So we'll have KD divided by let's say T plus KD. So this will be e raised power minus, what I'll do is that I'll just rub this off. So this will be again, you can take a moment to verify whether this indeed is the time response of the system subjected to a unit step input. Now, one implication of derivative control is immediately obvious. The original time constant of the system was T. Okay? The new time constant, that is the time constant of the closed loop system incorporating a derivative controller only, is now T plus K. Now, what we effectively have done is that we have increased the time constant of the system. So a system which was fast or reasonably fast in the open loop has now become slower in the has become sluggish. So this is the implication of this is one implication of derivative control. The other implication is that the steady state error in this case is quite large. So if you evaluate the steady state error, okay, which is essentially limit of t tends to infinity, e of t. Now you can carry out the algebraic manipulations, but you will see that the steady state error in this case will turn out to be 1. Okay, so in a derivative control, or in a closed loop system which incorporates a derivative only controller, the steady state error is always unity. Now this essentially means that the tracking properties of the system are abysmal. I mean, it's not a very good tracker. It does not follow the input at all. Now we can look for the reasons for this, why this is actually happening. If you plot the time response, you can see that the time response given by the previous expression is something like this. It looks something like this. So this, if I am not mistaken, this will be kd divided by 1 plus kd or t plus kd. Did I write t plus kd? So now, as was outlined in the previous class, a derivative controller actually produces a control action which is proportional to the rate of change of error. Now, as you can see, the rate of change of error is large only initially, that is at times close to t equal to 0. So, at times close to t equal to 0, the rate of change of error, we're not talking about the error, we're talking about the rate at which the error is changing, that is essentially very large. So a derivative controller produces good control action at times close to t equal to 0. But as t evolves, the rate at which the error changes becomes smaller and smaller and eventually becomes equal to 0. So as t evolves, a derivative controller essentially provides no control action. So as you can see, if this is the, if I show the input on this, which is, this is a unit step input. So as you can see, as t goes to infinity, the difference between this curve and this one essentially becomes equal to 1. So as t evolves, a derivative only controller will provide no control action at all, and the steady state error will always be equal to unity. So these are the implications of using a derivative only control. The performance is actually degraded. Okay, we make the system more sluggish, and the tracking properties too are not very good. So, hence, a derivative controller is never used alone in actual practice. You will always have it in combination with a proportional controller, or as a combination in proportional plus integral control. Okay, so I think that's it.